Swayam Prabha. Digital India. Educated India.
Welcome back to real-time digital signal processing course. So in the last class we are discussing about the discrete cosine transform. So we will continue today also on the discrete cosine transform. So in the DCT 3 we covered a little on quantization and then how we are going to have the quantization matrix to that is eliminate the lower part of the coefficients, that is AC coefficients in DCT matrix, and later on how we did the run length coding, and then in the process of recovering we will be using the Huffman coding. These are the things what we considered in the last class. So today we will see how we are going to consider the DCT implementation in hardware. So one of the application we said it is in JPEG applications. So that is in the analysis program that will be running on the, that is our UW parallel computing labs cluster has the thing, and then potential uses are in the in this lab what they use is for the application is in the agriculture, that is webcam is images can be analyzed for fruit that is ready to be harvested, and workers can then save time by only going to areas that have fruit. This is one of the examples or application what it is given in the web basically, and the other application what they use it is in the parking. So what is that? It is webcams can be placed in a parking garage, and their images can be used to identify areas with open spaces. So this is one of the example. In the parking lot you can identify if there is any empty space, then you can go and park your vehicles there. The other one is in the web search. What is that? Images can be found over the web that are similar to an input image, and images can be analyzed then stored as keywords to be used in searches. So all we usually type the basically for web searching, and if you are interested in some part of the images, if you have liked the thing, so you want to see that similar ones, then you can keep that as a reference, and then you can find out how many of them are available. As an example, in some of the applications if you want to run your machine learning algorithm, you need lot of images of that variety. So it is in that case it helps us to give up search for the typical those images. So as you can see in the agriculture, so that is how you are going to sort the image according to amount of red as compared to a baseline photo. So you will be seeing that whether you want to segregate them. So that is based on the red, if it is intensity is more you want to have it as first, and later on the next one, and then which has the minimum. So this is one of it. So this will show that some of the ripe fruits if you want to go and then pluck it. So you can concentrate on this area to pluck them. So little whatever later on you know that how long it will take for this tree to get more ripened one, and then here you are not seeing any red in the thing. So you know that fruits are not ready in the thing. So you can predict also and then see only those places what you can go and then pluck it, so that you will be saving some of the time of farmers. So we know that this is how we have introduced our DCT, that is discrete cosine transform. So we know that it is going to store the cosine waves, reduce them to a set of coefficients what we have given the values here, and we know that JPEG uses an 8 by 8 DCT. So, this is the this thing what we will call it as 8 by 8 our reference image, basically basis function what we call it. So, we will be having 8 by 8 basis function to find out our we will call it as coefficients. So, visual band as a wave what it is shown here. So, this is from the Wikipedia source, what you can go for more detailed one in that to see it. So, now coming to the human vision. So, what is it? We said already in the previous class, the better detect differences in light and dark than in color images. As you have, this is a RGB image. So, we have red, green and then blue. So, if you bifurcate them as luminance as we discussed in the last class, so you will be seeing that you are able to identify the person in that is Y component. And then chrominance, that is CB and CR, they are little faded. So, what we said was we can do the compression in this domain. So, that is what it is given. Luminance and CB and CR are the chrominance values and can be subsampled first basically. So, what is the subsampling we are going to do it? So, we are going to keep the chrominance Y0, Y1, Y2, Y3 as it is, that is and then we can do 2 by 2 that is subsampling, chroma subsampling. So, how we are going to do averages CB and C value to save space basically. Common sampling ratios are 2 by 1 in the horizontal, or we can have 2 by 2 both horizontal and then vertical. Okay. So, what we say is cheap cameras, that is webcams, mostly use this 2 by 2 standard subsampling basically. So, these are the CBCR. So, you will be subsampling to either 2 by 1 or 2 by 2. So, as it says, webcams convert it into 2 by 2 for cheap cameras. So, what is that? That is what it says is JPEG minimum coded unit. So, this is the smallest amount of data that can be coded in a given JPEG. So, how do you say that? That is size is going to depend on subsampling. So, if we are doing 2 by 1, then it is 16 pixel by 8 pixel what has to be stored. So, if we are considering 2 by 2, then it is going to be 16 pixel by 16 pixel what you will be taking it. So, this is an image taken from NASA, what it is projected to show that how the subsampling can be done. So, to give you a JPEG, the steps that are involved in summary. So, first what we do is a color space conversion. So, from RGB we will be converting it into luminance, chrominance and the BCR basically, and then we will be doing this chrominance subsampling is going to happen. Then later on we are going to do the DCT. So, we know that just the DCT is not going to give us the reduced size of the image. Later on we will go for the quantization. So, as we said in the previous class, quantization we can use p is equal to 1, 2 or 4 depending on how many values you want to store it. So, that is decides the quantization, how much you want to have it. One has to be careful that near the edges, so we may lose the information. So, one has to look into that when you are doing the quantization. Then once the quantization is done, so we will be in the DCT we will be going for the run length coding. In the IDCT, because we have to reconstruct the image, so we will go for the Huffman coding what we had discussed in the last classes, and then the reverse process is going to happen, that is whatever the quantized signal has to be requantized, and then IDCT what we will be doing it, and then we will go for the chrominance subsampling in the reverse direction, and then we will convert from YCR BR to RGB image, and then we will be displaying it. So, this is how JPEG in summary looks like. So, now we will see that how we are going to implement this in hardware. So, to give a again a flavor of what is DCT and IDCT, the code has been given, that is one dimensional what we are considering it. So, we have E of k into n is equal to 0 to n minus 1 x of n into cos 2n plus 1 pi k divided by 2n. N is we can choose it as 8 by 8, or it will be the size of the image what we are considering. So, if it is we are using it in the direct DCT form, k will be going 0 to n minus 1, that is our image size, n by n what we have considered here. So, in the reverse process IDCT we consider 2 by n, instead of multiplying by root 2 by n in both the cases, we consider only in the IDCT form 2 by n. So, this will be going from 0 to n minus 1. So, it will be E of k into x of k what you have computed, and cos 2n plus 1 pi k divided by n, and n will be varying between 0 to n minus 1 in this case, and our constant E of k is given by 1 by root 2 if k is equal to 0, and it is going to be 1 for other coefficients. Now, we will see how we are going to derive the thing. So, the first is we will take a 4-point DCT, that is simpler, just how we did for n is equal to 4 for our DFT. So, we are considering this, and then we will be expanding our summation so that we can combine our coefficients. Okay. So, the first is x of k is E of k is equal to n is equal to 0 to 3, x of n this equation, and k will be varying between 0 to 3. So, now x of 0 we know that 1 by root 2 summation of x of n. So, which is given by 1 by root 2 into x of 0 plus 1 by root 2 into x of 1, so on 1 by root 2 into x of 3. So, all the x 0 to x 3 has to be summed, and then we have to multiply by root 2 to get x of 0. To get x of 1, so we will expand the thing this equation by substituting n is equal to 0 to 3 in this case. So, which is going to be x of 0 into cos pi by 8 and x of 1 into cos 2 pi by 8 plus x of 2 into cos 3 pi by 8 plus x of 3 into cos 7 pi by 8. So, we are substituting n is equal to 0 to 3 in this, assuming our k is equal to 1. So, now what we call all these are cos functions what we have, we call it as coefficients. So, if you want you can expand x of 2 and x of 3 also to get 0 to 3 coefficients. So, here this is x of 3 what you have to expand it and then write down those coefficients. So, now coming to in the matrix form, if we substitute these values as we have got it expanded one. So, we will see how it is going to look like. So, my capital X of 0, X of 1, X of 2, X of 3 are written here, and we know that the first coefficient is going to be 1 by root 2. So, which is going to be multiplied by X of 0, X of 1, X of 2 into X of 3 as the input. And then the next second row is going to be pi by 8, 3 pi by 8, 5 pi by 8. So, you will be adding 2 pi for all the things. So, the last one will be cos 7 pi by 8. So, you will be seeing in the third row it is going to start from 2 pi by 8, and then you are going to add this thing, what is that 4 pi to this. So, you get it as 6 pi plus 4 is 10 pi and then 14 pi. So, because that is multiplication what we have it 2 into 2, because x of 2 what we are doing it 2 into 2 is 4. So, it will be plus 4 pi. So, it is going to be 6 pi, same as that. Now, the next one is cos 3 pi by 8, and then you will be adding 6 pi to that. So, 3 into 2 is 6. So, it will be 9 pi by 8 and so on. Okay. So, now because we know that we can simplify this. So, when you write the after simplification, So, what we are going to get it? So, in terms of negative, what you will be representing, because you will be doing 2 pi plus 4 pi. So, which is nothing but minus cos 2 pi by 8. So, by substituting all this, these are the coefficients what we will get it. So, we say whether it is symmetric or asymmetric rows, what we are going to have it, fine. So, now coming further, continuing with the matrix form. So, we will represent, we call this as a C2 coefficients, what we can represent for 1 by root 2. So, the next one is pi by 8 is C1 coefficient, 3 pi by 8 is C3 coefficient. Now, we can represent this as minus C3 and then this is minus C1. So, the next stage is going to be C2 coefficients cos 2 pi by 8 and then minus C2 and then C2. So, the same way the last row what we can represent it as C3 minus C1, C1 and then minus C3. So, we will know that 4 point DCT needs 4 coefficients. So, that is C1 to C3 n minus 1 coefficients, that is what it is going to be used. It is shown here, n minus 1 is 3 coefficients, that is C1, C2, C3 what we need to represent our coefficients here. Okay. So, some of the new variables how we can modify the thing is, so what we have is here we know that it is C2, this is x of 0 and we have rewritten the thing. Now, what is our x of 0? We have to sum up all this and multiply by C2, and same way what we will be doing for x of 1 is, it is x of 0 minus x of 3 into C1 plus x of 1 minus x of 2 into C3, because we will be combining this C1 and then this C1 and this C3 and this C3. So, that our number of multiplication is going to reduce. So, it will be x0 minus x3, we will subtract this and multiply with one coefficient. Same way for the other thing. So, you will be seeing for x2 and x3 the same way, you can combine them. So, now what happens? So, we will write it as from what we have is original we need, because it is a 4 by 4 matrix, we need 6 multiplication. So, what we can reduce this one to 6 multiplications what you are seeing it, that is 1, 2, 3, 4, 5 and then 6. So, we have reduced from 16 multiplications to 6 multiplications, but addition is going to remain the same. So, now we will see intermediate products how we will be representing it. We call it as x of 0 is given by P0 plus P1 into RC2. So, what is P0, which is going to be x0 plus x3, and then M0, that is because we are calculating the negative part of it, x0 minus x3, and P1 will be x of 1 plus x of 2 and M1 is represented as x of 1 minus x of 2. Then we will be reordering thus. So, we will be seeing x of 0 is given by this equation, x of 1, x of 2, x of 3 in terms of P0, M0, P1 and M1 is given by this equation. So, how we are going to represent in the butterfly form? So, we know that x0 and then x3 is going to be minus. First one is x0, we are going to take this one x3 to this, x0 plus x3 is my P0 output, and then later on x0 minus x3 will be my M0. Same way we will put it for x1 and then x2. So, that is x1 plus x2 will be P1 and x1 minus x2 will be my M1 here. So, what has happened here? We have the reversed input order just like our DFT. So, we are having x0, x3, x1 and then x2. Right. So, coming to the second stage, what is the thing is going to happen? So, we have P0 and M0 and P1 and then M1. So, next stage is we have X0 is P0 plus P1 into C2. So, we will be multiplying with C2 coefficients in the last stage. After adding with P0 M0, we will be getting X0. So, the next one is what we have is X of 1 is M0 into C1 plus M1 into C3. So, you have to have a M0 with C1 coefficient and then M1 with C3 coefficient. So, this is what you will be C3 coefficient. So, you multiply both of them, add them, you will be getting your X1. Now, X2 is what? P0 minus P1 into C2. You are taking P0 here minus what you are going to do, P1 multiplied by C2 will be given output as X2, and X3 we know that M0 into C3 minus M1 into C1. So, what we have M0 into what we have is here it is multiplied by C3 here and then M1 is multiplied by C1. So, after this is a subtraction, that is minus what we have it. So, we will be getting X of 3 as the output. This is how we can write our butterfly structure. So, the final thing what we have 4-point DCT is given by this complete butterfly structure. X0, X3, X1 and X2 are the inputs. So, we will be getting actually input is going to be small x0, x3, x1 and then x2. Output is going to be capital X0, x1, x2, x3 in line with our FFT what it is shown by combining these two butterflies. So, intermediate you will be seeing that P0, M0, P1, M1 and these are the output you will be seeing they are in order x0, x1, x2, x3 and input has got reversed in this case. So, now extending the same thing from 4-point to 8-point how we did with respect to DFT. So, we will do it for 8-point DCT. So, you will be seeing that input that is output is capital X0 to X7, input is small x0 to x7 what we have it. In terms of coefficients you will be seeing that from C2 because it is n by 2 what we are going to have it, that is 8 by 2 is 4. So, the first row is going to be C4 coefficients you will be having it. After that you will have C1, C3, C5, C7, C9, C11, C13 and then C15. So, you will be writing this way, fine. So, all the coefficients you can write it in this fashion and then later on as we see the symmetry thing what you will be looking into the thing. So, we will be reorganizing my, you will be seeing that my C10 is going to be minus C6. So, how many coefficients I need it here? Can you guess it? We said in 4.33 coefficients, in 8-point we need only 7 coefficients. So, that is C1 to C7 what we are supposed to have it. So, we have to organize in that manner. When we do that you can see the simplified matrix what it is given in this case and then you will be seeing that these are the outputs and multiplied with x0 to x7 in order. So, how we are going to represent this in a matrix form. So, one of the famous thing is what they call it as ACF and then BDEG coefficients form to put it in FPGA. So, you can use the butterfly structure last I will be showing it, otherwise most of the FPGA implementation use this format. That is we call it as instead of x0 output will be y0, y2, y4, y6. So, this is our DCT even coefficients what we are going to combine with the coefficients ACF. Okay. So, that is what for the even and you will be adding x0 plus x7, x1 plus x6 and x2 plus x5 and then x3 plus x4, and these are the odd coefficients bottom. So, you can put them in bottom y1, y3, y5 and then y7. So, they need BDEG coefficients to compute, and the input to this will be x0 minus x7 and x1 minus x6, so on, and this one. So, now to compute with these coefficients back, okay, IDCT. So, how you will be using in the that is y0 to y0, y1, y2, y3, what you will be calculating it. So, you will be using the ACF coefficient in the top portion, but you will be seeing that input is going to be that is bit reversed, that is x0, x2, x4, x6, not completely bit reversed in this case. Even anyway, what you will be considering it here same as our FFT. So, here it will be x1, x3, x5 and then x7, what will be using the thing, and then when you multiply with this BDEG coefficients and add them up, you will be getting the y0 to y3. Then what you are going to do is do the same thing, but you have to subtract with this BDEG coefficients which are getting multiplied with odd numbers. So, you will be getting the higher, that is y7, that is y4 to y7. So, you will be seeing that it has come in the reverse order. So, y7 will be first and then y4 will be coming later on. So, this is how you would be reconstructing with the same coefficients both in DCT what you will be using it and then in the inverse DCT also. How we are going to do that? So, you will be putting, that is if you are putting 8-bit 1D DCT, when you are putting in this format. So, that is y is equal to our matrix A into x, the matrix with coefficients whatever we have discussed in the previous one, that is ACF and then BDEG. So, you will be seeing that all these are A coefficients and these are BDEG minus G minus E minus D and minus B, and then the rest of the coefficients are getting filled like this. You can go back and then cross verify it, and then which are what are the our ABCD FG coefficients. So, it is nothing but root 2 by n. So, A is cos pi by 4, B is going to be cos pi by 16 and C is this one cos pi by 8, and then G is going to be cos 7 pi by 16. So, this is for the 8 by 8 matrix. So, you can substitute, it will be much faster and then computation. So, the symmetrical property of that is what the DCT coefficients what you have seen the thing, IDCT after adding it, DCT part what we said by multiplying it what we will be getting it. So, the same thing again it is shown that how from IDCT DCT or DCT to IDCT what you will be traversing with the same type of coefficients. So, how the architecture in FPGA is going to look like. So, this will be X is the input, that is we call it as data recorder unit, and then we will be having the ACF matrix vector multiplier and the other one is BDEG matrix vector multiplier, and then we are going to have the inverse data recorder unit basically, that is output is going to be Z coming out of it, and then what is Z? So, the same data you will be doing the transpose the memory and then get it as Y and feed it in the reverse direction. So, this is our ACF matrix and this is our BDEG matrix. So, you can go from a Y to X or X to Z. So, this will be transposing and then putting it as input and then we will be working it out. So, this is how the hardware implementation is going to happen in FPGA. This is data recorder unit in the thing. So, you will have the transpose of memory and you have the ACF matrix vector multiplier, input will be coming to here and this output is going to be given to our inverse data recorder unit here, and we will be doing the transpose and then we will be getting the BDEG matrix vector multiplier and then we can feed it in and then we will be taking the output from here. So, if you are using it in the DCT, you can use it in one direction, and then if I want to have the IDCT, the same hardware is going to be used in the reverse direction as we pointed out in the thing. So, to give you a flavor of how the 8-point DCT, I want you to work it out how much we have reduced in the 1D DCT with the butterfly structure. So, you will be seeing that these are the stages what we are going to have it S1, S2, S3 and S4 compared to log to n stages in FFT. So, we will be having log to n plus 1 for 8 point, as you can see there is SY stage also will be coming in the art side part of it. So, this is our x0, and then you will be combining with minus S7 input A and B, what you will be showing it as a matrix 4 point, what you can take it and then put it across. This is the even side, this is the odd part of it. So, I want you to work it out so that the output is going to be V0, V4, V2, V6. So, input is in order, output is going to be in the bit reversal format, what you will be getting it. The odd side you will be seeing that it is V1, V5, V3 and V7, and these are the sine and cos function. So, if those are interested in this paper, I will be uploading it in the thing how they have reduced number of multiplications and additions, so that it comes to 13 multiplications in this case. One more paper reduces from 13 multiplications to 11 multiplications with 27 additions along with it. So, this is how you can implement it in hardware, that is butterfly structure with cos and sine functions what it has been given, and then you can see that to the normal DCT output, whether this output for the 8 point what you will be getting it. So, this gives the complete summary of the DCT in hardware. So, have a happy learning and then thank you. Hopefully, you have enjoyed this course. So, we will do the summary of the complete course in the next class, what all we covered it, and then we will discuss how we can implement it in hardware, and then how we have done our labs and other sessions based on the theory part of it to verify our outputs. Thank you.